So hi, I'm Josh Saxe. So my day job is I'm chief data scientist at Sophos, and the talk I'm giving today is entitled "The New Cat and Mouse Game: Attacking and Defending Machine Learning-Based Software." So I'll start by just introducing where I come from, my team. So that's me on the upper left. These are all the people who I work with. So our group's a mix of machine learning scientists and also engineers who help build prototypes. And our role within Sophos is we build machine learning models that go into our firewall products, into our sandbox product, into our endpoint security products, that kind of thing. We are hiring, so if you're interested, let me know. Okay, I'll start with an outline of the talk. So I'm going to start by discussing why I think machine learning security matters a lot. So I'm going to talk about the increasing role of machine learning in the technology landscape. Let me go on to sort of set up my discussion of machine learning security by just giving a brief overview of how I see what machine learning is, just in case there are machine learning sort of neophytes in the room, to make sure everybody's on the same page. Then I'm going to talk about machine learning attack and defense, go into a little bit of the academic literature on attacking and defending machine learning models, and then finally I'm going to give a case study where I show how I can attack a machine learning model that we actually built and are using at Sophos, and talk a little bit about defense also. Okay, so let's get into it. So this quote is a play on the common sort of tech aphorism, software is eating the world, which maybe some of you guys have heard. So this is the idea that since like the 80s and 90s, right, you're seeing software pop up in unexpected places, and it's sort of ubiquitous throughout our society, whether it's in the fast food industry or in hospitals, right, places where software wasn't a key factor, now it is, right, and so we care a lot about software. Wherever it pops up in software security as security experts, right? So I think we're going to be seeing machine learning popping up everywhere in a similar way over the next couple decades. So one way of framing this, right, is that we've had a series of industrial revolutions over the last couple of centuries, each of which was driven by a new technology, right? So steam power in the 18th century, mass production driven by electricity in the late 19th and early 20th centuries, then the IT revolution that our generation has sort of lived through. And a lot of economists and technologists are saying, and I tend to agree with them, right, that we're going to be seeing over the next few decades a big shift in the way that we live our lives and run the economy based on machine learning and artificial intelligence, whether it's the transportation industry, right, with trucking and self-driving trucks and cars, whether it's education, right, and new education platforms that rely on machine learning, et cetera. So machine learning is going to be more important, and thus machine learning security is going to be more important. So our community tends to see cybersecurity risks everywhere software exists, right? And I think we're going to be seeing, increasingly we're going to need to sort of learn more about machine learning and think about the cybersecurity risks that pertain to machine learning as well. Okay, so before talking about machine learning security, I just want to back up and give some machine learning basics. How many of you guys would say you're pretty fluent in the way, say, like neural networks or support vector machines work? Okay, that's what I was hoping. So a lot of people aren't. So hopefully this will be helpful to you guys. Okay, so to try to illustrate some of the basic ideas behind machine learning, I'm going to walk through a toy example. Since this is a security audience and we're all security people, I'm going to walk through a use case where we build a machine learning system that detects malware. So to get into this example, so imagine I want to build a malware detector that just uses 3 attributes of software binaries to detect whether or not the malware is a binary is malicious or not. So let's say these 3 attributes are how compressed a file is, how big the file is, and the number of printable strings in the file. So if let's say I have a data set of files and I extract these attributes from the files, I can plot them in this 3-dimensional space, right? And suppose my malware is all sort of in this area of the 3-dimensional space, and my benignware is all in this area of the 3-dimensional space, right? So the red dots here are malware, and the blue dots here are benignware. Then I can pose the machine learning problem as a sort of as a mathematical problem, right? Of identifying a plane, right, that separates the blue dots from the red dots, right? So we can pose it as a mathematical problem, then the problem is to solve it. So in the image I just showed you, there's a plane that separates the examples. In the real world, usually we need to find a much more complicated function, right? So like these lines in this image separate the green dots. Let's call those benignware, and the red dots, let's call those malware, right? And the mathematical problem is to find a function that defines all of these lines here. Let's call those lines decision boundaries, right? Because we're making a decision. If you're on this side of the boundary, right, you're benignware. If you're on that side of the boundary, you're malware. Is everybody with me so far? Okay, so there's sort of geometric intuition to how machine learning works. So obviously, so this is a two-dimensional case where we have two features. This is the three-dimensional case. In real world machine learning systems, you've got like thousands of dimensions, right? So you can't visualize them, but it's the same geometric ideas that drive it. So how do we create a decision boundary? I'm gonna show, if technology cooperates here. Maybe I won't show a video. Let's see if this works. There we go. Okay, so here's a video in which we watch a neural network, which is shown on the right, learn as part of a training process, right, a good decision boundary for different data sets, right? So what you're seeing is sort of in each of these animations, the neural network starts out by not having a good decision boundary separating the green from the blue dots, and then as the training process goes on, right, it sort of learns how to separate the green from the red. How does this learning process work? I think a good intuitive way of understanding it is through this knob metaphor. So imagine these knobs on the left. If you sort of tweak them, they change this decision boundary in the image, right? So sort of like an Etch-a-Sketch, but with like a million knobs, right? So you're sort of moving the knobs, and the decision boundary changes position. So the problem is to turn the knobs into just the right position so that the green dots are, the benignware is separated from the malware. So how do we know how to turn the knob? So in neural networks, which are currently an important sub area of machine learning, the way that we learn, the way that we do it is through some simple calculus, basically, and this iterative process called stochastic gradient descent. So the basic idea is that we can use some calculus to determine for all of the knobs what direction we should turn them in and to what degree. But the calculus isn't perfect, right? So we can't just solve the problem by doing that. We'd have to take sort of a little step, and then we look to see how good the decision boundary is, and then we take another little step by running the calculus again. This process is called, figuring out what direction to turn the knobs in and to what degree is called we use an algorithm called backpropagation to do that. And then actually, in the iterative process by which we sort of turn and check is called stochastic gradient descent. There's a lot more depth than what I'm giving here, but this is just an intuitive description of how it works. So the two simple ideas that I just described, right? The idea of a decision boundary in this geometrical space, and the process by which we learn the decision boundary through this sort of knob tweaking and learning process, are really the foundations under which the complex and modern neural networks that are used at like the Facebooks and Googles of the world work, right? So you get these really complex neural network architectures, like the one shown in this image. This is a famous neural net called AlexNet. That's a computer vision neural network. So it involves like dozens of layers of neurons, thousands of neurons, right? But the whole system really is like what it amounts to is it identifies a decision boundary between the different types of images, and it's tuned through this sort of knob tuning process. Okay, so I'm going to move on from, so that's sort of my brief spiel about how machine learning works. I'm going to move on to talking about machine learning security now, and specifically subverting machine learning classifiers. So subversion of machine learning systems is in the current state of the art is it's quite possible to subvert machine learning systems, and it's relatively easy. So to sort of dramatize that, I want to walk through an example of the way an attacker can subvert a computer vision system. So look at these images here, and we're going to talk about a computer vision system and the way in which we can trick it into thinking this school bus is a different kind of artifact, right? So imagine I'm an attacker, and my goal is to get a computer vision system to confuse the school bus for an ostrich, right? So a bird. So the way I do that at a high level, right, is I compute a delta to all these pixels. So for each pixel, a small sort of change that I'm going to change to its magnitude. So the delta is pictured here, right? So this is what I'm going to add to all the pixel values in this image in order to get a new image that's going to confuse the computer vision system. And what I have here on the right is the new image that results from taking this image, adding this specially crafted delta, right, and then getting this new image. And it turns out that there's really no visual difference to the human eye between these two images, but the one on the left is classified with high confidence by the computer vision system as a school bus, and the one on the right is classified with high confidence as an ostrich, right? So this is interesting. I mean, so this is a toy example. In the real world, case, you could smuggle porn onto Facebook or wherever you're violating somebody's terms of service by using a delta like this, and computer vision systems would miss it, right? You can make your way through spam filters that look at images, right, by subverting them in this way. So there are real world consequences to being able to subvert computer vision systems in this way. So let's go back to the decision boundary idea and sort of think about how this attack works in a more mathematical sense. So suppose we have this decision boundary and it separates sort of the world of images between sort of the school bus territory and the ostrich territory, right? So if you think about it this way, so all of these red dots, right, are images of school buses that our machine learning system has correctly sort of placed in the red zone, right? So it gets the images right, and all of these green dots are examples of ostriches, right? And the machine learning system has sort of learned to discriminate between the two based on this decision boundary. So the goal of the attack, right, is to take an image of a school bus and sort of shove it somehow over into this green zone without changing the way it's perceived by the human eye, right? Everybody following? And so how do we do that? So it turns out we can use the same kind of mathematical ideas that we use in the training process for the machine learning system in order to craft a delta, like what I showed, in order to shove the example over the decision boundary. To do the basic attack shown in the school bus example, you need access to the model code and all of the model parameters. Basically, you need access to the model. And so in the real world, you can't always do that, right? So if I'm attacking like Facebook, or like if I'm attacking like the Gmail spam filter, right? I don't actually, unless I've hacked into Google servers, right? I don't have access to the model. So that's an issue for an attacker in the real world. There's a way around the problem of having to have access to the model, though, which is what we can call a proxy attack. So basically, if I have access to, let's say I don't have access to Google's spam filter, but I can send millions of emails through the spam filter and see what gets classified as spam and what doesn't. Then I can actually build a model that attempts to replicate the results of Google's spam filter, my own machine learning model, and then I can do this attack. I can do the school bus attack against my own model. And it turns out that attacking my own model, which has been trained to mimic the Google model, actually will reliably get through. At least in experiments, it's been shown that it can reliably get through the Google model. So this is sort of called a proxy attack. So I've been talking a lot about images and the way we can subvert computer vision systems, and I haven't been talking a lot about programs, right, like malware versus benign programs. And this is because it's harder to subvert systems that classify malware versus benign. And the issue is that, so with images, images gracefully degrade, right? I can change every pixel value in an image and shove it over the decision boundary, and it'll look visually similar to the original image. With a program, I can't go and change every byte value, right? It just won't run. And a malware author who wants to subvert a machine learning based malware detector has two problems, right? They need to get through the machine learning system. They also have to have their program work, and it's much harder to accomplish that. It's hard to accomplish that task, right? So it makes it trickier to get. It's still very possible, but it makes it trickier to get programs through machine learning based detectors. I'm not going to talk too much about the academic literature on attacking and defending machine learning models, but I just want to give you guys a sense of the back and forth and the back and forth that's going on in the academic literature about how to attack and defend machine learning systems. So for example, the school bus attack is sort of based on ideas that come from Ian Goodfellow, who's sort of a superstar in the machine learning security space. He came up with a method that uses model gradients, so it requires access to the model to subvert machine learning classifiers. Somebody else came up with a defense called distillation that people were excited about and appeared to work. And then somebody else came out with a paper, defensive distillation is not robust to adversary, so that actually shows that doesn't work. You can tweak the gradient-based method in a small way and you can get past it, right? So we're seeing there's a lot of interest in this area right now amongst computer scientists, and you're seeing a lot of back and forth, and it's basically defending against these kinds of attacks is an unsolved problem, basically. And like many things in the security field, right, I think attackers have the advantage right now. Okay, so the last thing I'm going to go through is a case study where, so the background, a case study where I attack and defend a security machine learning model that we have in our group at Sophos. The background to this is we've started a project within our data science group where we're going through and attacking our machine learning models. So the models we actually have out in deployment and models that we plan to deploy, just as a kind of red team exercise, and then we're working on figuring out defenses because we want to be prepared for potential attacks that happen in the wild. So the target is a model that I've presented before at conferences. So it's the exposed neural network. This is a neural network that we use to detect malicious file paths, registry keys, in URLs. So it's part of a larger defensive system that we have at Sophos. Here's some examples of the kind of URLs that the system detects, right? So if you look through these URLs, right, the first one is a URL that points to a Trojan SVC host.exe. The second one is a phishing URL that attempts to steal people's Apple login credentials, and the third is a PayPal phishing link, right? So if you guys look, so these look suspicious, yeah? If you guys look, okay, so they obviously look suspicious. So they look suspicious to the human eye. So our idea was that, you know, a machine learning system should also be able to detect that they're suspicious, right? And it turns out, I'm not going to show accuracy results, but it works well enough that we're, you know, it's a model that we use internally at Sophos. So I want to demonstrate how, if I'm an attacker, I can get past this model. So I'm first going to show some naive attacks against it. So my goal as an attacker in this case is to craft a phishing URL that will trick like my mom or, you know, my grandpa, right, like into clicking on it, but which also gets past the classifier. So I can't just randomize too much about the URL, right? It needs to look like a convincing phishing URL, but it also needs to get past my neural network. So I'm going to start this demonstration by just making up a phishing URL. So this actually isn't a real phishing URL. I just made it up. Wells Fargo customer support.webhosting.pl. It looks suspicious to the neural network, right? It gives it a 97% probability of being malicious. So here's a naive attack against this neural network that actually doesn't work, right? So I take my URL and I append some random suffixes, right? And the hope is that it'll make the score lower. But it doesn't, right? Actually, the score stays about the same or even gets a little bit higher. So a random suffix doesn't work. Now let's try some, instead of random suffixes, some sort of benign words like Disneyland, walrus, and jacaranda, right? So I have the same URL, I just tack these words onto the end. Again, it doesn't work. Fortunately for me, as the researcher who created the neural network, right, the neural network is resilient to this kind of attack as well. Now let's try. So the more sophisticated approach that I tried was I created a genetic algorithm that systematically sort of searches the space of possible suffixes and sort of iterates over thousands of examples and sort of evolves suffixes that do well at lessening the score. And after about 50 generations of evolution, so after having tried 50,000 examples, right, I can get the score down to 43% and 57% with these suffixes, right? They don't look that different from the random suffixes, but they were evolved through this genetic process. And if I take the evolution even further, so I double the number, so I get up to 100,000 of sort of examples that I've tried, I can get the score down to 8%, right? So basically, at this point, the neural network thinks the URL is benign, even though it looks like a phishing URL, right? I mean, it still looks suspicious, right? So it's that, I would say that attack was successful. Just to give some insight into the genetic algorithm, obviously I can't cover this in the 25-minute talk, but the basic idea with genetic algorithms is that I'm modeling my suffixes as individuals in the population, and I go through a series of generations. So I start out by creating 1,000 random suffixes. I look at the ones that minimize the score as much as possible, and I mate them. So I combine sort of their character sequences. And then I do another generation where I try them again, and through this evolutionary process, I get good suffixes. In the animation, you're seeing individuals in the population, and just to sort of carry the example further, the idea is that every generation, the ones that survive are the ones that get higher up on this hill, and let's think of the hill as my ability to minimize the score that my URL classifier spits out. So I also explored some defenses to my attack. The best defense I've come up with thus far is pretty unsophisticated. Basically, if I retrain my model on a different subset of my training data, the attack no longer works. So we have a lot of URL training data at Sophos. So we train our URL model on about 100 million URL examples. About half of those are malicious and half of those are benign. So it's not so hard for me to I can subset 50 million of those. And I can have multiple. If I wanted to just train on 10 million, right, each, I could have 10 different models, right, and they're somewhat resilient to this genetic algorithm attack. So basically, my score goes all the way back up if I train on a different subset of the data. The problem with this approach, right, is that I'm not training all my models on all of the data. So the model performance is going to suffer as a result. So I don't think my solution is perfect, but it's the solution I've come up with thus far. So I just want to end with I have 2 minutes left, so I want to end with some common sense wisdom on defending against adversarial attacks. So I'd say I think it's important to attack your own models and see where their weak spots are and fix them. Don't give attackers access to your model if possible. That makes it easier for them. Don't even give attackers the ability to query your model with thousands of examples. Like, so don't give them black box access. That also makes it easier with the proxy attack that I showed earlier and the genetic algorithm attack I just showed. Use layered defenses, defense in depth, helps, right? No system is perfect. And if for those who are machine learning researchers and computer scientists out there, I would say this is a really interesting area to work in right now. It's a hot area and it's a high impact area, I would say. So do research in this area. So that's it. Thanks a lot. And I don't know if there's time for questions and comments. Okay, yeah.
The slide where the score was changing, right? So how does the attacker get access to the score?
Yeah, so I'm assuming the attacker I'm assuming the attacker doesn't have the model codes or the model software, but can query the model. So like say for example we released the model as a web service within Sophos, maybe like a paid web service for our customers, and the attacker could get access to that. They could upload 100,000 URLs and get the scores back. They would need to be able to really brute force the system and get scores back for all of their URLs before they could get through it. So yeah, you'd have to be able to query the model a lot. So that's one limitation the attacker has in this case. Yeah.
But practically, would make sure it's on. Is there a difference between being able to query the model for legitimate reasons, like I buy a license and I can query the model, versus I buy a license and I query the model maliciously?
Sorry, can you? Yeah.
Like, if I bought the software, I could be buying it to defend my network, or I could be buying it because I want access to the model so that I can attack the model itself.
Yeah.
And is there a way to provide the model, or how do you provide the model for positive use versus without allowing the negative use?
That's a good question. I'd have to think about it. That's a good question. Yeah.
And you said that training on different sets of your data helped defend it. Did you look at bagging using, a bagging type approach using multiple models, and did that work?
Yeah. So in this case, we're not doing bagging. So the hand wavy wisdom about that in a neural network context is you can sort of get the same effects as bagging using a technique called dropout, which adds noise to your neural network. So it's just not something we baseline all of our models with like a bagging approach called random forests, right? And this outperforms random forests. So yeah. Cool. Yeah, go ahead, yeah.
So for your genetic algorithm, for each iteration, are the URLs fairly similar, like just a few characters different, or are they drastically different overall?
So you mean when they mate?
Yeah, exactly.
Are they very different?
Yeah.
I don't know. It was okay. Kind of a quick. I probably spent 2 days on it. I never actually inspected I never introspected into the algorithm to see how similar they looked. I will say that the successful, if you watch like the leaderboards as the solutions evolved, like you'd get a lot of regularity, and like it would wind up finding like these character subsequences that just like stuck around generation after generation. So I would say probably there was a lot of similarity between the parents and the children.
Cool. So that might be a good way to go for the defending that Gabe was asking. Like if you get a lot of queries that are very similar, then maybe.
Just like.
The line talk yesterday.
Yeah, exactly.
Yeah. Mm-hmm. Yeah, so you're saying if there's some like global minima that the optimizer is finding that we could just like whitelist, like, basically just like whitelist away or something, or like train on, like that would help defend against this attack, right? Like,
or even just watch the queries.
Uh-huh.
If like the person makes similar queries over time, then you can sort of like treat it as an anomaly.
That makes sense. Yeah, that's a really good idea. Yeah.
So are you using a web reputation service, or are you using this as a replacement for it?
So they would be. I mean, I don't want to speak to like Sophos's product plans. I will say that they're right now. I mean, Sophos, has a reputation service. The role of this neural network is there's a separation of concerns, right? So the reputation service is for stuff we already know about. This URL model is for stuff that we don't know about yet, right? Stuff that is not on a blacklist, because it's not detecting based on hash rate; it's detecting based on the semantics of the URL. Does that make sense? Like So I think it's complementary to a reputation service. You definitely want to block stuff that you know is bad. You also want to block stuff that you don't know about yet, and that's what the neural networks for the latter problem. Yeah.
When you showed the slides where some of the Euros got caught and the others did not get caught, what was happening in the back end in the neural network that caused that difference? It seemed that they would have been the same.
That's the $1 million question. Yeah. So, I mean, these, neural networks are like kind of famously black boxes. It's hard to know why they do what they do. We try our best so we've got some work like Rich here is like doing some work on explaining why they make decisions when they do. But right now I would say I don't know. It's a mystery. Yeah. Thanks.
What are the features that you trained the model on, or did the neural network derive the features on its own? Yeah,
so in this case, the neural network, you could say, derives the features. We feed in basically just like the integer, ASCII kind of. They're using Unicode, but basically we just feed in the characters, and then it discovers what useful.
What kind of neural network is this?
So it's a convolutional neural network. We could talk about it more. We also have a paper about it. I could give you the link, but we can talk more about it afterwards. Yeah.
Nice. Thank you.
Mm-hmm.
All right, we are out of time. Just want to, if there are any more questions, please feel free to follow on peer list, folks. And thank you very much.
Thank you.